So, implementing the dual simplex algorithm. We have, at this point, we've, in some cases quickly, in other cases in more detail, stated the algorithms and proved that they're correct, except for finiteness, and we will get to that a little bit later in the context of some of these implementation ideas. So, first of all, some motivation. Why am I looking at the dual simplex algorithm? Reason number one, about twice as fast as the primal. It's much more important in practice for that reason alone. Second, and this is one of the big driving reasons, the dual is the best algorithm for mixed integer programming. So in mixed integer programming, you are constantly solving linear programs while you're processing the nodes of the tree. And the dual simplex method is a good algorithm in that context for two reasons. First of all, when you're processing these nodes, typically you've just solved a linear programming problem, and then you change it a little bit by changing a bound or maybe adding a cut. So the fact that you're changing it only a little bit means that you can usefully use the information from the last solve to resolve the next problem. You can take the basis in particular and construct a new basis for this slightly modified problem, and typically that basis is close to optimal. The simplex algorithm is really good at re-optimizing from a basis that's just a little ways away from the optimal solution to quickly get to the optimal solution. Interior point algorithms, the alternative that's not mentioned here, are terrible at doing that. They're just, for this reason alone, in almost all cases, impractical to use them in the context of processing the nodes in the mixed integer programming problem. So, those methods are gone. That leaves us with primal and dual. Simplex dual dominates the primal in terms of performance, and in addition, the nice feature, many of you will be aware of, inside of MIP is that when you add bounds, change bounds, or add cuts, it will destroy primal feasibility, but it doesn't destroy dual feasibility. So you can not only restart the dual and re-optimize, you're re-optimizing from a feasible solution. You don't have to repair feasibility. You put all those things together, the fact that dual is faster than primal, that it has restart capabilities, and that you typically actually are restarting from a dual feasible solution, it's the choice that you want to make. So that's primary motivation. And the final motivation for talking about the dual is that you're hard-pressed to find in books descriptions about how to implement the dual. People just don't talk about it. Maybe because it's harder to talk about. It is certainly easier to motivate the primal. I absolutely agree with that. But that's not the algorithm that gets used so much. Okay, dual simplex algorithm. Here it is restated. And I don't think you can see the colors so well. There's supposed to be some red stuff there to emphasize the parts we're going to talk about. So you have to get a dual feasible basis to run this thing, so we have to figure out how to do that. There's the pricing step, which says to take, here it says to take the biggest infeasibility. It's actually not a very good idea. We'll propose something that works better. So that'll be an implementation idea. We have these two linear systems to solve. These are large, typically sparse linear systems. A few years ago, we discovered there was a way to enormously speed up those two steps. We're going to talk about that. The ratio test, which determines a step length and a leaving variable, is actually a wonderful idea that was, I think I'm saying some of the things that are going to be on the next slide, actually. It was a wonderful idea that goes back to a woman by the name of Paula Harris, who worked for British Petroleum, wrote a couple of papers in 1972 which are almost unreadable. But they each has a very clever, nice idea. Both those ideas are used today in modern simplex codes. So she knew what she was doing, she just didn't know how to write. Okay, so here's my little list. Number one, implementation issues. Finding an initial feasible basis or concluding that there is none. That's sort of phase one of the simplex algorithm. That's the typical designation for it. Pricing, we will talk about something called dual steepest edge, which has made a huge difference. Then we're going to talk about solving linear systems and the things that are involved in doing that in the right way. In particular, we will talk about these FTran and BTran things. By the way, BTran stands for backward transformation, and FTran stands for forward transformation. The origin of those names actually goes back to the old punch card days, when literally all these codes and all the data was on a big stack of punch cards, which you ran through a machine in some order. And what somebody discovered is if you do stuff, you put your deck of cards in, the forward transformation, you could run the cards in this direction, and you didn't have to pick them up and turn them around. If you just ran them back in the other direction, you could do BTran. So they called it FTran and BTran, and the names have persisted. Though, fortunately, punch cards are no longer with us. Numerically stable ratio test, which led to an idea called bound shifting and perturbation, which simultaneously makes the algorithm more stable in both the primal and the dual, by the way, and also takes care of degeneracy, all in one idea. It's actually one of my favorite things to talk about. It's not a complicated idea, and I think everybody, all codes use it now. And finally, something that we call bound flipping. Sometimes this is referred to as the long step dual, which will come right at the end. We'll see if we have time for that. That's probably the least important thing on this list. Okay, preparation, bounds on variables. So we've talked about standard form and we've had non-negative variables, but in general we have to talk about general bounds on variables. Real problems have upper bounds, they have lower bounds. The algorithms have to accommodate that. And some of the little implementation ideas that we want, you can't even talk about them unless you talk about bounds. So we have to introduce them. And here's a problem. This is what a typical real problem actually looks like. Minimize C transpose X, subject to AX equal B, and upper and lower bounds on the individual variables, where some of the lower bounds may be minus infinity, some of the upper bounds may be plus infinity. That's allowed. Now, obvious observation. You could take these bounds and absorb them into the constraints and get back to standard form and apply the simplex method in that way, and that would be a really stupid idea. Okay? It's much better to handle the bounds separately as bounds. But if you really want a slow implementation, which you can then subsequently improve, be my guest. Okay. So, a basic solution. What is a basic solution for a problem that has bounds? We define it in this way. A basis P is a triple BLU, where B is an ordered M-element subset, just as before. And BLU is a partition of 1 through n, such that Lj, the lower bound, is greater than minus infinity for everything in L, and it's less than plus infinity for everything in U. So you may notice I've assumed there are no free variables. Every variable has some finite bound. Okay? We'll come back to that. So the associated primal basic solution is given by setting all the things in L to their lower bounds, all the things in U to their upper bounds, and then computing the values of the basic variables, which you do by substituting the lower bounds in, substituting in the upper bounds, adjusting the right-hand side, and using the fact that this thing has an inverse. The solution is feasible, obviously, if XB lies between its bounds. The associated dual basic solution is defined exactly as before. So, you know, you got to go through details to convince yourself this one-to-one correspondence still holds and so forth and so on, but it does, just like we said before. So you can think about a basis in the primal, and there will be an associated one in the dual. The associated dual basic solution, you set dB equal to 0 for this B. You set, and you solve for pi, and then you compute these so-called reduced costs or dual slacks. And the thing is then dual feasible. Dual feasibility becomes more important. This is the statement of it. You need to be non-negative on the things at lower bound and non-positive for the things at upper bound. Time does not permit going through the derivation of this. It's not hard, but it involves writing a number of things. The intuition is pretty simple. You've got a basis. You can think of it in the primal if you like. You've got some variables non-basic at upper bound, some variables non-basic at lower bound. If something is at its upper bound, it should be an unwise thing to reduce it, right? Which means you want the reduced cost to be less than or equal to 0. So that reducing it would increase the objective in the primal, where you're minimizing. And similarly for things at the lower bound, well, there the condition doesn't change. It was non-negativity in the previous case. So really the only difference is that for variables that are set at upper bound, their dual feasibility corresponds to those things being less than or equal to 0. Okay. So, bounds on variables, the full story. This can't be true. I'm sure I'm not going to tell the full story. Starting to sound like a politician. So, modify simplex algorithm. Only the pricing and ratio. Oh, yes, I know what this is. So, okay. So we've got bounds. Now, legitimately, I should go back to these primal and dual and state them with bounds. It's a mess. Literally stating the dual with all general bounds in it and so forth, it is a long statement to get it right. And to convince yourself that it's correct is a long and frankly boring exercise, so we won't do it. Kvatal's book, it's an old book at this point, but in my opinion has a very nice description of the primal simplex algorithm with bounds. It's easy to translate that, straightforward, to translate that into a description of the dual simplex algorithm with bounds. It's complicated, there are details, but there's no magic involved in this. Right? So if you want to implement it, you do need to go through that. You do have to implement it with general bounds and take advantage of those bounds. So I'm going to obviously skip these details. Okay, initial feasible basis. This I am going to talk about. 2 parts to the solution of this problem: finding some initial basis, probably not feasible, and then modifying the simplex algorithm to find a feasible basis from that starting basis if the starting one is not feasible. Idea number 1 is an old and simple idea. It is basically introduce artificial variables. So this one you know. Let me describe it in the primal, because right, the primal and the dual, there's a one-to-one correspondence. So if I tell you how to think about it in the primal, it then corresponds to a basis in the dual. So what do? I'm going to assume every variable has some finite bound. There are no free variables. Simplifies the statement a little bit. I'm going to add artificial variables. And what does that look like? Pretty straightforward. I take ax equal b and I just add one variable to each constraint. I've labeled them n plus 1 because there are n variables here, up to n plus m because there are m constraints. And now, it seems kind of silly, but I set the lower and upper bounds to 0. Right? So I haven't changed the problem at all. But I've done this nice simple thing of introducing an identity matrix, which is, of course, non-singular, and I can choose that as my initial basis. I don't have to worry about inverting something and checking that it's non-singular. So the initial basis you take is just this list, n plus 1 up to n plus m. And for each non-basic variable, you just pick some finite bound and put that variable into L or U, whichever. If you've got a variable that has both an upper and a lower bound, typically what one does is puts it in the set with one of those 2 bounds that's smaller, because that somehow perturbs things a little bit less. So that's just a simple, practical choice. Go through the variables in the original model, and if they have just one finite bound, they go in the set that they have to go in, L or U. And if they have 2 finite bounds, put them in the set that would give them the smallest absolute value. So that gives us our initial basis. For free variables, the simple refinement that I believe almost everybody makes is to make free variables non-basic. This is really cheating. Non-basic at the value 0. Non-basic variables are supposed to be out of bound. Free variables don't have any bounds. So you have to pick some value, and the convenient value to pick is 0. And then you make one modification in the simplex algorithm, which is those variables are now allowed to move either up or down, not just in one direction. And that primal, for example, gives you a corresponding simplex algorithm. So let's leave those free variables aside and now look at the question of getting a feasible basis for the dual. Did I do this right? Yeah, that's the right slide. Okay, so we're thinking about the dual. We know there's a one-to-one correspondence for bases between the primal and the dual. So if I describe a basis for the primal, I've got a basis for the dual. I just described to you a way to get a pretty simple basis for the primal using artificial variables. That gives us a starting basis for the dual. If it's feasible, fine. Okay? And in fact, let's think about it. One of the reasons, actually, that the dual algorithm has an advantage over the primal is that it's easier to get a starting feasible basis. In fact, I claim if every variable, as an example, if every variable in your problem has both an upper and a lower bound, it is trivial to get a dual feasible basis. Why? Start with an artificial basis, then take every variable in the problem which either goes into the L set or the U set. But since both bounds are finite, every variable could go in either one of those sets. So compute the values of the dual slacks, and depending on the sign of the dual slacks, put it into the appropriate set, automatically capturing dual feasibility. So there is a trivial dual feasible starting solution, easy to write down for any problem in which all variables have both upper and lower bounds. For example, a purely combinatorial problem where you're dealing only with binary variables. The LP relaxation, every variable is going to have a lower bound of 0 and an upper bound of 1. There's always an easy dual feasible solution for those problems. Right? And for the primal, it typically is not an obvious dual feasible solution. Okay, so returning to the general case, where we have a basis, it's not dual feasible, we want to fix it. Here's what we do. Here's what I propose doing. I claim this problem at the top is equivalent to determining whether there does exist a feasible dual solution, basic or otherwise. Right? And it simply says, take the constraints of the dual and maximize over the solutions to those constraints the sum of the negative entries from DJ. Right? So the biggest that can be is 0, obviously. And if it is 0, all of the DJs are greater than or equal to 0, and therefore I've found a feasible solution to the dual. Right? So if I optimize this, I will get a feasible solution to the dual or prove that none exists. The only problem is what I've stated up here is a nonlinear problem. It's got strictly less than, the objective is moving around depending on what the DJ values are. So it looks like this is a hard problem to solve, but in fact, this problem is locally linear. That is to say, suppose I have actually a basic solution to my problem, and I compute the values of the variables. I can then identify the set of J indices where I have a violation to dual feasibility, and all the rest. And I can write down, at least at this particular solution point, a linear objective that tries to force these negative things to be positive. And that's this objective, kappa, where kappa is equal to 1 on exactly the negatives. All right? So as my solution moves around those kappa values, this objective are going to change. But at that snapshot, at that point, it's a linear problem. Okay? So it's a linear problem. I've got a basis for it. I assumed I had a basic solution. Basic solution doesn't have anything to do with the objective. has only to do with the constraints. So it's still a basic solution. I can apply the simplex algorithm to it, and actually all you need to do is make one simple modification. You take a step. If in the process of that step, one of these D's moves from infeasibility to greater than or equal to 0, you change its kappa. It can only happen after an iteration has been completed, because things go to bounds. So the iteration is completed. At the completion of the iteration, you stare at the objective, change it where it has to change, you get a new linear representation, you do the next iteration. So you have a linear local representation, do a simplex iteration. It changes, do a simplex iteration. It changes, do a simplex iteration. You're doing simplex iterations, and you can prove that that will either converge to a feasible solution, and hence a dual feasible solution, or you will prove that the minimum is not 0, which shows that there is none for the original problem. So there's some work to do to prove that, but in fact it does work. Okay? So that's the idea of the algorithm. And one beauty of this algorithm is that, yes?
So this might be a stupid question, but currently defining one phase of the dual simplex algorithm and takes one step of this one phase using the dual simplex algorithm. That sounds circular.
Yes, I'm in phase 1, which means I'm trying to find a dual feasible solution. And I'm describing to you how to take one step of that. Can be viewed as an instance of the simplex algorithm, and then I propose repeating that.
So I think
Did that answer your question?
I think he's thinking about whether phase 1 means phase 1.
Huh? He's thinking about whether...
Whether phase 1 of the simplex algorithm needs a phase 1 to begin with. You know, that it's circular.
Is it circular? Okay, so I'm not concerned about the name. I have to admit I'm confused by the question. Wouldn't be the first time. My wife thinks I'm always confused by all questions. So, this is nothing new for me. The fact is, I think I'm proposing something that at each step involves using the steps of the simplex algorithm to carry out one step of this procedure. But each time you go back to the start, the objective function might have changed. Okay?
But I think they're worried about using the algorithm in the first phase of the algorithm. But at this point, you don't need the first phase.
I got it. Okay, now I understand the question.
Yeah.
I got it. Okay, here's the answer to your question. I have tricked the algorithm into believing that I have a feasible basis by declaring variables that are less than or equal to 0 feasible. I changed their bounds. So right at that instant, it looks feasible because I said the bound is less than or equal to 0. I changed the objective to try to make that go away. But it's a good question. Sorry it took me so long to get it. So again, the question is, wait a minute, I don't have a feasible basis. How can I be applying the simplex algorithm? But what I've done is I've locally changed the definition of the problem so that it is feasible to a different problem, which allows me to carry out an iteration of the simplex algorithm. And then I repeat that. Okay? So it really is true, if once you've written the code, this is the way the code structures, once you've written the code to do an iteration of the simplex algorithm, none of that changes. It's just each time you feed into it a slight change in the problem. The algorithm, literally, nothing changes. It's the same algorithm. It thinks it's feasible because you played with the bounds. Okay? So, thank you for that question. That's actually a very good question. So we're going to go one step with this. I'm going to show you an improvement to this which actually contributes significantly to the stability of the whole procedure and speeds it up. It's a little bit tricky. I'm going to go through it quickly and we'll move on, but it really does help. So, suppose dBi is the entering variable. Then xbi less than 0, where xb is obtained using the following formula that's how I select an entering variable. So, this funny problem that we're solving where we've tricked the bounds, the formula for the values of these xb's, it's a funny formula. I got to tell you, that formula doesn't mean anything to me. I only know one way to get it, and that is just to do the algebra and compute it. There's a definition for how you compute these things. You just compute it using the dual, and this is the formula you get where this kappa, that's that objective. That's changing from one representation to the next. But it's a 0, 1 vector. It's a simple vector. It's just changing all the time. Suppose now that dj is determined to be the leading variable. Then in terms of phase one objective, this means kappa j is replaced by kappa j plus epsilon times ej, where epsilon is in 0, plus 1, minus 1. All that's saying is that as this objective changes, it's just changing from plus 1s to minus 1s as we go across boundaries. Okay? So the changes that are occurring are very simple. And now, the crux of the idea here is the following. In the normal simplex algorithm, when a variable hits its bound, you got to stop. Because if you go any further, you make the problem infeasible. But in this case, it's perfectly legal to cross those boundaries. You can take a variable that's feasible and make it infeasible, or one that's infeasible and make it feasible. As long as the total infeasibility is decreased, that's all you care about. So this allows you to loosen the ratio test. You go to the boundary. Now, you just have to think for a second. Why did I make this step? I made this step because this thing was, the fact that this was negative told me that was profitable in terms of improving the objective. It was moving me in the direction of feasibility. So all I have to do as I cross the boundary is update this value. If it's still negative, it's still a good idea to continue in that direction. And that's what you do. And the update formula, which of course you have to derive, takes a few minutes, involves only this number alpha j, which is a vector out of a vector we've already computed. You don't have to compute anything new. The number is known. And this alpha j, what you discover is that alpha j is actually what's known as the pivot element in updating the basis inverse. And so actually, if alpha j is a really small number, you don't want to do that. You also don't want to get wrapped up in all these cables here. Actually, I was giving a talk once in Amsterdam. This was back a number of years ago in the days when they didn't have all this fancy stuff. And I actually had a microphone with a cable on it that I was holding. And I was on the stage walking back and forth as I always do. I totally lost track of where I was. And by the time the talk was over, I was wrapped up in cable like a mummy. All these people were afraid I was going to just fall off the stage and do some damage to myself. Some of them might have actually hoped that would happen, but in any case, it did not. That danger has subsided somewhat. That's nice. So the point is that precisely when alpha j is small, you are likely to conclude that xb has not changed sign, and therefore you can make a longer step. And you avoid that pivot element, which is numerically good, and reduces the number of iterations. If it's large, then the sign may change, but that's okay because that's numerically stable. So you reduce the iterations and you increase the stability in phase one. This is the kernel of why that algorithm on the previous slide, in my view, is a good idea. Right? So that's phase one. It was not simple. I wish I knew a way to make it really simple. So much for that. This is a brand new topic, and so what we just talked about plays no role. This has to do with pricing in the dual. So let's see. The rule that's stated in the algorithm, as I stated, said take the most negative or the biggest violation of the primal variables, the most negative, xb. Right? That turns out to be a really bad idea. It corresponds to the same really bad idea in the primal of taking the most negative reduced cost. Here's why it's a bad idea. Now thinking geometrically helps. I'm at a vertex. I'm trying to decide which edge I'm going to go along. What the reduced cost measures is the rate of change of the objective per unit that I move along the axis. Per unit that the variable changes, not per unit along the edge that I'm traversing. If that edge has a big angle with the axis, a small movement on the axis is going to look like a big movement on the edge and is therefore going to blow up the reduced cost. You're going to think it's helping more than it is. What you really want to do is measure the rate of change of the objective per unit along the edges. All right? Now, there are various ways to do that. The ideas really go back to Don Goldfarb. He's the guy who has really understood this idea of steepest edge. Back to some papers. I think his first paper on this was 1974. He and John Forrest wrote a very nice paper in 1992 in which they described a whole bunch of different steepest edge algorithms for the primal and for the dual. And I say a whole bunch of different ones. You say, well, wait a minute. Didn't you just say we're supposed to measure along the edges? There's a trick. You can take your polyhedron and you can project that polyhedron into a different space, onto a different set of variables. Maybe get rid of some variables that you don't think are so important in some sense. In that new projected polyhedron, it has edges, and you can do steepest edge in that projected space. And what they discovered is that you get simpler formulas, faster formulas to update for different projections. And in fact, in the dual, they discovered if you project out the slack variables, you look at only this thing in the space of the pi variables, you get this formula for a number. It's a complicated looking formula. If you scale the xb values by this thing and take the most negative of those, you are doing a version of steepest edge. And in addition, they showed that there was a very efficient update formula for these particular numbers. Because you can't recompute those numbers at every iteration. That involves solving a linear system. It would just kill the whole algorithm. So you need to use the numbers to scale the xb values. That improves the number of iterations. And to make it practical, you have to give an update formula for this thing, which is in the paper. You'll look it up. The end result of all of this is that all of the standard implementations of the dual that I know of, their default is to use some version of this steepest edge in the algorithm. Interestingly, there is no correspondingly efficient steepest edge for the primal that anybody has ever found. Nobody has ever found a projection that works quite as well as the one that was used here and gives you simplified, fast-to-compute formulas. So even though primal and dual are mathematically equivalent, here's another sense in which they are not equivalent. So I'll just give you one quick example. This is a problem. It's an old model. It's not so hard anymore. It used to be considered very difficult. If you use greatest infeasibility, it takes 281,000 iterations in 118 seconds on whatever machine I was using 2 days ago when I did this. And if you use the steepest edge algorithm, it takes about 20,000 iterations and 5 or so seconds to solve. And I will finish this description of steepest edge with one remark, and that is one of the remarkable things that happens with this steepest edge. It not only reduces the number of iterations, surprisingly, it speeds up the iterations typically. Even though you're doing more work, it speeds up the iterations because it seems to be much smarter about picking a sparse path around the polyhedron than the greatest violation pricing algorithm does. So it somehow wins on both dimensions. It's just, in the end, a no-brainer. And it's a simple thing to implement. It doesn't change anything in the algorithm except the scaling and the pricing step. Okay. Solving FTran and BTran, and I think I need to get done here so that Toby has a little bit of time left this afternoon. So there are two parts to be discussed here. You need to solve the linear systems. You need a basic method for solving them, and we want to then speed it up. We never compute inverses. I said that already before. If you've done any numerical analysis, you know you never compute inverses. It's numerically unstable, and it also will kill you in terms of sparsity. So what people do is implement LU factorization as the basic approach to solving these linear systems. There's actually a paper published in 1990 by Uwe and Lena Zuhl. And actually, what was implemented in CPLEX many years ago, what I did, I just took that paper and I implemented it. Actually went and talked to Uwe Zuhl a couple times, got a few additional ideas and implemented it. And to my knowledge, it's more or less what still gets used, and it's more or less what gets used in Gurobi. So if you just go to that paper and implement what's in there, which is a dynamic Markowitz approach to computing an LU factorization, you will have a pretty good factorization. All right? Close to what state-of-the-art codes use. Updating the factorization. So this again is a standard idea, an old idea, not special to the dual, and I'm not telling you something that anybody in this subject doesn't know. You don't want to compute a new LU factorization at every iteration, it's too expensive. So you do what's called an update. There are various kinds of updates you can do. Kvatal's book does a nice job of reviewing the updates that are available. The simplest is a so-called product form update, which goes back to about 1950. And actually, as a first implementation, it works pretty well, especially if your problem is very sparse. So you can quickly get a product form implementation. It's simple to implement. What the codes use these days is a version of the Forrest-Tomlin implementation, which is an LU factorization. And again, I would refer you to Kvatal's book. In my view, he gives a very nice description of what that algorithm looks like. If you implement simply exactly what he says for Forrest-Tomlin, you will get something that's pretty close to what the good codes have. Where the work is on really, really sparse problems, making Forrest-Tomlin as fast as product form, and that requires finding a few tricks in the way things are moving around. But the basic implementation is as described by Kvatal, and the remaining part is, as I say, involves looking at the combinatorial structures that arise and taking advantage of them when the problem is really sparse. Okay, now to show you the main thing that is not so well known, though it's becoming certainly more well known, is related to solving these linear systems, FTran and BTran. So I've written them down here. BTran involves a unit vector on the right-hand side, so that's certainly very sparse. FTran involves a column of the constraint matrix on the right. Those are typically also very sparse. And I just give you an example here of a problem. This is actually an LP that came from a traveling salesman problem. It's got 85,900 constraints, that many variables. The average size of this vector that you're computing is only, in that problem, 15.5. It's a small number. A tiny number compared to this 80,000. So you put in something small here and you get something small out. You absolutely must exploit that to do things in a smart way. Actually, a bit of the history here, up to the point that problems had at most 5,000 to 10,000 constraints in them, what I'm going to show you didn't make any difference. It was only when it started to get up to 50,000 and 100,000 that this one computation I'm going to show you started taking 90% of the time. And if you tried to solve a million row constraint problem with the technology that existed before the idea that's on the next slide, you literally would spend 99.9% of your time in one silly step inside of solving these two systems, which I will now show you. So here's a picture. I've got an LU factorization. I want to solve a linear system, AB times Y equals AJ. And the way you do that with an LU factorization is you first solve L times a newly introduced vector W, LW equals AJ. When you get that result, you solve UY equals W, and that gives you the vector Y that you need. And since the two matrices are triangular matrices, you can solve them by back substitution. So it's a straightforward exercise to solve them. This picture here is going to describe to you what that solve looks like. So here's my input vector on the right-hand side. The x's are where the non-zeros are. The way those things are stored, I know where those x's are. This problem could have a million constraints, but only 3 non-zeros, and I know where they are. Don't have to search for them. W is what I'm trying to compute. Here's how I proceed. I go down x to the first non-zero, I know where it's at. I go across to the corresponding variable and to the corresponding diagonal entry, which is not 0. I divide this number, the x, by the number on the diagonal. That gives me the value of this variable. I then plug in that value, multiply it by the non-zero entries in this column. I know where those are, if I've used any kind of reasonable data structure. And I update the right-hand side. When you update the right-hand side, you introduce potentially new non-zeros. So now I have to search through that vector on the right-hand side to find the next non-zero, which in this case would be here. That step, amazingly, searching for that next non-zero, if you don't do it in the right way, that will take 100% of the time in the whole algorithm. Just that one step. Here's how you can avoid it. There's a simple graph theory idea, a beautiful little idea that takes care of it. Works like this. Define an acyclic digraph, the nodes of which are indexed on the rows of the problem, and you put an edge in this, a directed edge in it, if the entry Lij is not 0. Because in a lower triangular matrix you only have entries where I is greater than j, this will be acyclic. All the arcs are going to go in one direction, okay, from increasing to decreasing index. Define x to be the set of all indices for which Lij is, whoops, this is wrong. Yeah, this is wrong. This should say the set of all indices I for which Aij is not 0. I'm sorry about that. So this is, x records where the non-zeros are on the right-hand side. Then you do a reachability calculation. You find all the vertices that are such that there is a directed path from those vertices to x. It's easy to implement that algorithm, like a little computer science exercise. It runs in time linear in the size of the set that you're after, plus the number of edges that you traverse, which really corresponds to the number of non-zeros you have to look at here anyway to do the solve. This set x bar is exactly the set of entries that you will have in the end on the right-hand side. So you compute that in linear time, you can sort it, and now you're done. You know exactly where the next entry is going to be. You don't have to search for it. Here are some examples. Here's a, oh man, Toby's going to kill me. Toby, are you here? He's not here. Huh? He's out committing hara-kiri somewhere, I suppose. Yeah, okay. Anyway, well, I'm almost done. I really need to show you this example. It's so cool. So, this goes back to 1990. This is back when Interior Point and Simplex were competing with each other. The military in the U.S. had a bunch of models they wanted to solve. And they concluded at that time you could actually solve them better with Interior Point algorithms than you could with the Simplex algorithm, and wrote a paper about it. These models were, they had a whole series of them related that I wanted to solve, all the way up to actually PDS 100, Patient Distribution System 100, that they wanted to solve. And at that time, 2 and 6 were easy, 20 was a challenge. So everybody was looking at PDS 20, trying to solve it faster than all the other guys. So I went back and I ran these with the 1988 version of Cplex, Primal Simplex. I did this a number of years ago on some machine. And actually, so these are in seconds, right? So this is 30,000 seconds is a third of the day. So anyway, you're talking about a long time, right? I actually went back and calculated PDS 70. If you had tried to solve this in 1990 with this Primal Simplex algorithm on the then available machine, it would have taken 10 years. So this comes back to your point about testing old algorithms on old machines. It doesn't make any sense. Computation time, literally what you can show it would have been 10 years. So probably somewhere in there you would have decided, I should maybe think of it a different way. Same machine moving forward, dual simplex. So Interior Points were winning, but all of a sudden dual simplex was faster. And then came along Cplex 8.0, which included that idea that I just showed you. and the times plummeted. So this is now the right way to solve these models. Here are the speed-ups, but more important than the speed-ups are this graph. This is a graph of the solution times with 1.0 as a function of the size of the models. These models have the property, this is the 2-period version, 6-period, 10-period, 20-period, 70-period. The periods are like little blocks. The size of the problem goes linearly in the number of blocks. Not surprisingly, you would expect, as I increase the number of blocks, the number of iterations would grow linearly in the number of blocks. And the number of rows grows linearly as the number of blocks, so the time per iteration you might expect would grow linearly. Well, iterations grow linearly, time per iteration goes linearly. The product of those two is quadratic, and indeed you see that here quite distinctly. Computation time grew quadratically. Moving to the new version, here it's plotted completely different scale. The times are much lower. These are the Cplex times. Look at that. It's qualitatively different. It's not growing quadratically, it's growing linearly. In other words, number of iterations was growing linearly, but the time per iteration stayed constant. Because we were smart about finding the non-zeros, the fact that there were a bunch of blocks made no difference. The algorithm just went right past it. And I updated this with Cplex here. With Gurobi here, you see it's really dead on linear. And this is what saved the simplex algorithm for large problems. Without this idea, it's dead. And with this idea, you can solve large problems that are sparse. You're in the game. Right? This made a huge difference. Okay, ratio test and finite. I really need to get done here. I'm absorbing the whole day. So let's see if I can get through this fairly quickly. This is an important idea. Ratio test and finiteness. So we're doing the dual. Feasibility in the dual means these D's are non-negative. But in practice, we replace that by a different condition where we allow each of them to be slightly negative, typically about 10 to the minus sixth. Why do we do that? Why do we introduce this so-called feasibility tolerance? The reason is most real problems, all real problems, are highly degenerate, which means even though these variables, you've got variables that the basic ones that could in principle be positive, most of them are zero. You solve a linear system, and if you solved it exactly, you would get zero. We don't solve them exactly, which means some will be slightly positive, some slightly negative. If you don't allow for them to be negative, you'll conclude everything is infeasible. It wouldn't work. So you are forced to introduce this. Paula Harris's idea was exploit it to make the algorithm better. And so what she did is she proposed an alternative to the standard ratio test, which I have listed right here, which essentially takes the old step length that we computed, computes a new step length, which is larger based on this epsilon, and now says pick anything in between, maximizing the size of this alpha, and thus improving the numerical stability. So this simple idea, explained here very, very quickly, improves the numerical stability. But it introduces a problem. It's a bit of a subtle problem. It takes you a while to recognize that it's there. But when you implement it, you see it. So it's more stable, and it actually does reduce degeneracy. It tends to let things be slightly negative, tends to get you away from being stuck by degeneracy and zeros. But if it happens that your entering variable is less than zero, then the objective goes in the wrong direction. So I need to explain this briefly. I've got a variable. Variables that are not in the basis need to be fixed at a bound. But suppose when it was in the basis, it was slightly negative. Well, I was thinking that it was going to be decreasing from positive down to zero, and now all of a sudden when it leaves the basis, it goes from negative to zero. So you thought you were going to improve the objective, and suddenly it went in the wrong direction. And you just implement this in a straightforward way, you see the objective starts oscillating on you. It literally took me, it took me about a month to realize there was a really simple solution to this problem, which was fundamentally to cheat. And the cheat was the following. If that variable is less than zero and it's going to go in the wrong direction, The lower bound is 0, change the lower bound. So I just went and changed it to some number that was less than what it was and made the direction the right direction. That made the objective monotone. That was wonderful. The problem is, of course, in the end you solved a different problem. You didn't solve the problem you started with. And that's where the combinatorial nature of the simplex method rescues you, because even though the numbers are wrong, you have a basis. That's a combinatorial object. At the end, you can reset the variables to their proper bounds, and what you discover in 95% of the cases, you get lucky, and you actually solve the original problem. Amazing. So you've improved stability, you've actually automatically improved degeneracy, and in the end, you typically don't pay anything for it. Now, some numerically difficult problems you do pay for it. You have to remove the shift and re-optimize, and this example illustrates a case, I won't go into the details, where it's happened twice, and the way Gurobi handles that is removes the shift, switches from dual to primal, which is now feasible, and iterates that process, and I don't have time to go into the details. But the shifting, yes?
Can we characterize when this happens, and or would it be possible and thus avoid trying it to become?
Avoid?
Basically, if you know that you will produce something infeasible, not do the shift?
No, I wouldn't know a way. So if I understand your point, it's like, okay, I'm changing these bounds because I don't want to go in the right direction. If I know that in the end, removing that change is going to introduce this infeasibility, why don't I just avoid it there by some procedure? I don't know any way to detect that in advance, short of some massive computation. And it so rarely happens. It just turns out it's not worth worrying about, as far as I can tell. I mean, I was quite amazed at this, and I felt pretty stupid when I finally realized how simple it was. But anyway, the simple ideas, I guess, are the good ones. And by the way, this immediately rolls into the idea of perturbation. So in essence, this is a kind of perturbation. So what do we do, by the way, if problems are having, if a problem is having difficulties with degeneracy, which we would measure by saying the objective function is not progressing fast enough. So you put in something that measures that the objective is not progressing fast enough, and then all we do is we take a pseudo-random number generator and generate a small perturbation that, decreases the lower bounds. It's just like a bound shift, except it's an intentional bound shift that's not forced by the ratio test. You do that. It's utterly straightforward. I don't know why people didn't, do this in the old days, if you will. And it works marvelously. And no new machinery is needed. You don't have to introduce any new machinery because removing the perturbation is like removing a shift. It's all the same. It all happens together, and all of these things contribute actually to reducing the iterations. Interesting property of the dual that doesn't seem to be shared by the primal. The dual actually seems to like to be perturbed. So Gurobi, and I suspect, and it was true at one point in Simplex, actually will perturb even if the problem is making reasonable progress, because it just helps the algorithm for some reason that we don't fully understand.
Sorry, Bob.
Yeah?
Shouldn't it read like minus epsilon plus epsilon j? Because then your total infeasibility stays between minus epsilon and,
You're saying,
otherwise you can end up with minus 2 epsilon.
no, you're saying this, you say,
Yes, I'm
no.
talking about this equation, maybe if it should be a plus.
No, it's actually supposed to be minus. So there's a trick here that I'm not telling you. In fact, there are lots of tricks I'm not telling you. Not because I'm trying to be secretive, because I'm lazy or something. So the point is, actually, the way I implemented this back in the old days was only to do a perturbation. Think of it in the primal. That's the simplest place to think of it. I would only perturb variables that were in the basis. And now I'm reducing the lower bound, and so perturbation is guaranteed to maintain the feasibility of the solution. And then the non-basic variables that could cause an issue, I perturb them only when they enter the basis. And so in the end, all variables get perturbed, and feasibility is preserved, and it should be a minus. Okay? So, I think I'm going to skip bound flipping. But it works. That much I can tell you. And I appreciate your time. Thank you.